Okay, so I'm gonna go over the quiz number 2. So make sure you take down the notes, take down the answers, so that way you have something to study from for the future. Okay, so quiz number 2. Okay, so you can now you just kind of follow along. Okay, when measuring circuit current, the ammeter is connected, so all the current flow through the ammeters. That's what was demonstrated yesterday on the assignment 6 and 7. So yeah, you break the circuit and force the current to flow through the meter, so you can get the collect the answer. The total current. So the answer is C as in Charlie for number 1. Okay, for number 2, the symbol to the right represent this. This is right here is a diode, and with this arrow pointing up, 2 arrow, that's represent LED or light emitting diode. So that's the answer is B as in Bob for number 2. Okay, number 3, clowning around in the laboratory can cause which of the following? A, yes, that's true. You can get electric shock if you touch it the wrong place. B, you can get burns. C, you can get cut or bruises from accidentally bumping into things. So the answer is all the above. So the answer is D as in David for number 3. So any question number 1, 2, or 3?
Yes,
Okay,
I
no
got a question.
Yes.
For number 3,
Yes.
wouldn't it be cuts and bruises?
When you're clowning around in the laboratory, yeah, you can get cuts and bruises, but you can also get burns depending on if you work at a solder station, you touch a solder, touch a solder tip, you're gonna get burns. And then electrical shock, if you're working with the 5 volt and the 10 volt, if you accidentally touch that, yeah, you definitely can get a light shock from that. Okay, so all this do occur if you're clowning around in a laboratory. You can accidentally happen, you can get a shock, you can get burns, you can also get cut and bruises, you can knock over chairs and anything like that. Yes, so the answer is D as in David for that's applied to all of them. Okay, all right, page down. Okay, number 4, why is it important to have permission to use the power tools for the first time? Okay, yeah, so mainly just make sure that before you do anything, you want to get the instructor, you want to follow the instructor instruction, because we already done, yeah, power tools do cost a lot. That is true. But there's people in the working shop, yeah, those are also, but everything doesn't matter where you go to, you have to listen to the first thing, follow the instruction from the instructors or whoever the lead in the shop. So the answer is C as in Charlie for number 4. Okay, so first thing, get the instruction from the instructor. After that, then you can start doing whatever you need to do. Okay. Number 5, safety rules should be obeyed in order to, okay, so yeah, so to finish the project as quickly as possible. Yeah, so because if you follow the rules, all that, there always deadline to do your job, to get things done, and then also to keep the student busy. Well, that is one of the small, one of the objective. Okay. And also to prevent injury to yourself and others. Okay, like I said, no clowning around in the lab, because you can touch into the chairs and bump into things and the computers, break the computers and anything like that. So the answer is D, all of the above. D as in David for number 5. Okay. Number 6, a term used to describe opposition to current flow is resistant. So that's the C as in Charlie for number 6. So any question number 4, 5, or 6? Okay, no question. Next set. Okay, the unit of measurement of electron flow is mainly ampere. Okay, current is measured in ampere. So the answer is D as in David for number 7. Number 8, current flow in a circuit is 0.015 amp. This value can also be expressed as, okay, so 0.015 amps, same thing as 15 times 10 to negative 3 amps, or 15 and then 10 to negative 3 is the represent the milli. Okay, so you can say 0.015 amp or 15 times 10 to negative 3 amps or 15 milliamps. So the answer that match one of these is B as in Bob for number 8. Okay. Number 9, the ability of a quarter watt resistor to give off heat is related to its, okay, so mainly you look at, mainly it's the physical side. So the answer is D as in David, because this was from the handout. As you can see, actual side of carbon resistor. So that's depending on the different type of, so you got the physical size. So you have an eighth, quarter, half, and you got a 1 watt and a 2 watt. Okay, so this one able to handle more heat. Okay, so physical side do matter. So number 9 said D as in David. So any question number 7, 8, or 9? Okay, no question. Next up. Okay, a color-coded resistor with bands of blue, gray, and black has a value of, okay, and the answer is B, as in 68 ohms at plus or minus 20%. So B as in Bob for number 10. You know that blue is represent 6, gray represent 8, black represent 0, none represent plus or minus 20%. So therefore 668, the first, this is first digit, second digit, and black represent your multiplier, which is this here, 10 to the 0. 10 to the 0, same thing as 1. So 1 times 68 would be 68 ohms. And that's plus or minus 20%. So the answer is B as in Bob for number 10. Number 11, the property of conductance is the ease of current flow. Okay, so 11 is D as in David. Number 12, the total voltage in the circuit shown is, the answer is A as 1.5 volt. Okay, so the answer for 12 is A as an atom for number 12. Okay, this is how you do it. So this is positive 12, positive 1.5 here. This is positive 1.5. This is positive 1.5. Now this is reversed the other way. So therefore it's going to be negative 1.5, and this also reversed against the flow. So therefore that's going to be negative. So this one going to get canceled, this one, and this one cancel out with this one, leave you just a 1.5 volt. Okay, the answer is A as an apple for number 12. Any question number 10, 11, or 12?
How did you get the negative?
The negative, you look at the current, you look at the flow of the of your battery. Okay, so this is going from negative to a positive, so that's positive 1.5, negative to a positive, so that's a positive 1.5. And this one is going to be a negative to a positive, so therefore it's going to be a positive. And here you're gonna, for this one, you're gonna from a positive to a negative, so therefore it's going to be a negative 1.5. And this one is going to be from a positive to a negative, so it's going to be a negative 1.5. Okay, you follow?
Yes, thank you.
You're welcome. Okay. Okay, any other question? Number 10, 11, or 12? No question. Okay, that's with color code. Okay, so number, oops, let me see, look like this one is February 12th. Okay. Okay, number 13, in any DC electrical circuit, voltage and current are directly proportional. That is just follow the Ohm's law, okay? So if you increase current, you're going to have to increase the voltage, okay? So they're directly related. So the answer is D as in David for number 13. 14, when you use any form of Ohm's law, how many values must be known, okay? So for any calculation, if you want to solve for E, for I, or R, you must at least know two other value with the two other variable, either current resistant, or voltage and resistant, or voltage and current. Okay, so we need at least two known variable in order to solve for the third one. So therefore, the answer is B as in Bob for number for 14. Okay, number 15. Hold on one second. Let me go ahead and go finish this and then I answer your question. Okay, 15. If an electric circuit has a current of 15.4 milliamps and a source voltage of 20 volt DC, the total resistance is, okay, first one, current is 15.4 milliamps. I have to convert that one to amp first. So that's 0.0154 amps. E, which is 20 volt VDC. So R equals E divided by I. So this one right here. So you want to do is E divided by I. So you calculate this resistance. Okay. So now look at this one. So E is 20 volt divided by 0.0154 amps. You do that calculation, you come up to 1298.7 ohms. The closest you can round it up to 1300 ohms. So A as an apple for number 15. Okay, what's your question, Mr. Smith?
Oh, yeah, I got it. It's basically an algebra thing. You need to know two things to figure out something.
Right. Well, this one you have three variables. You got the you have your current, you got your voltage and resistance. So you have to know two of them in order to solve for the third one.
Yeah, I agree with that. That's pretty much algebra.
Okay. Oh, sorry. Any other question? Number 13, 14, or 15? Okay, no question. Okay, number 16, Ohm's law is used to solve for the circuit. Okay, we just show you, we can do current, resistance, voltage. So the answer is D, as in David, all the above. Here it is, we can solve for voltage, we can solve for current, or we can solve for resistance. That's Ohm's law, okay? So 17, in electric circuit where the voltage is 100 volt and the resistance is 25 kilo ohm, the current is, okay, E equals 100 volt, R equals 25K or 25,000 ohm. And we put this one in to do a calculation, I equal E divided by R, so 100 volt divided by 25,000 ohms. That gives you 0.004 amps. And since that is not one other choice here, so I convert this one to milliamps. That would be same thing as 4 milliamps. So the answer is A as an atom for number 17. Number 18, when you connect a voltmeter to read a DC voltage, the voltmeter is connected across the component. Okay, so like we measure the power supply and all that, we measure when you're in parallel with that component or just across the component. Okay, so the answer is C as in cat for number 18. Okay, any questions? 16, 17, or 18? Okay, no question. Okay, back to you, Mr. Pham. Thank you.
Thank you, sir.
You're welcome.
Mr.
I'll have
Pham,
fun.
Mr. Pham,
Yeah,
I have a question before we get started on class about one of the Tech 2 homework assignments.
take your homework assignment.
Yes.
You know, we get the field, right?
Yeah, just a few.
Okay,
This
that's
is-
what happened.
Okay, let me share my screen here real quick.
Okay,
Okay, so it must just be something basic I'm misunderstanding. So here, according to the directions, we have a 3-bit binary number. The binary inputs are fed into a logic circuit that produces a high only when the binary number is odd. Complete the output Y.
then what?
So here on the truth table, we have 0 through 7 in binary in the inputs. Is that correct?
That's correct.
So should not the outputs read 0, 1, 0, 1, 0, 1, 0, 1 at the output? Since 0 is even, 1 is odd, 2 is even, 3 is odd, 4 is
Okay.
even.
Now, that means tomorrow I will be go over with the truth table. Okay. However, on that one, they given you 3 inputs. ABC. Automatically, you get the truth table. And the truth table will be telling you how do we get the output. Okay. And now they said, okay, output will be high when the binary number is odd.
Yes, sir.
Okay, so binary, let's see, binary number is odd. So the first one 0, correct? The second one will be 1. The next one supposed to be 1.
Why is that? Because the binary number on the inputs is 2.
No, they count on 1. That means number 1 is odd.
So what he's trying to say is you take C plus B plus A, and if it comes out odd, then it's you get a 0. If it's even, then it's 1. So you got 0 plus 1
Oh.
plus 0. So therefore it's 1.
Okay.
1 is an odd. Yeah. Hold on. Is it odd? Is supposed to be
That's odd.
high. Okay.
And I know the only choices are 1 and 0. So I know when I'm wrong, I know what the answer is. But I was reading it, I guess, like BCD, where you add a 0 to the end of it to complete a number. I was reading it like 0, 1, 2, 3, 4, 5, 6, 7.
Yeah, you're reading in a decimal notation.
Okay, so
Yeah.
here,
So therefore,
because
if we look at the binary notation, we just take those digits and add them together, and then at the end we have to define whether that one's going to be end up with even or odd. So therefore, if
Okay.
you look at the ones at 1, 0, 1, so you got the 1, 0, 1, the one that a little bit lower. One more, you want more
1,
line.
0, 1,
1,
right.
0. Okay, so you got 1 plus 0, that's 1. 1 plus 1 would be 2. It'd be 1 and 0. So you got this one. So 1 plus this, that would be 1. Okay, 1 plus 0 would be 1. 1 plus 1 would be 1, 0. Right? It's
Okay.
almost like a 10.
So we're using binary addition.
Yeah, you look at exactly. You look at more like binary addition.
Is
Okay.
that also considered 5? That's why it's odd, so you get 1.
Yeah, so therefore, yeah, and then after that, and then you can convert it that when you get that 10, and then that 10 would be 1 and 0 again, and that would be, yeah, and then that would become 1. So
You
that's
got to carry the 1.
Yeah,
we
so
don't
that's
care.
1, 0, 1. So there one, yeah, that's 0, and then you got plus 1, so that become 10. Or yeah, you got 1 carry over to the next space, and you got 0. So therefore, that would represent an even.
I got from top to bottom, I got 0, then 1, then 1, then 0.
Yeah, we know that you got your answer, Mrs. Smith, but can you tell the logic? How did you come up with the logic of getting that
Because
answer?
you got for the first one, obviously zeros. For the second one, you got you got 1.
Well, it's 3-bit, so technically isn't the A place a value of 1, B a value of 2, and C a value of 4? So it's just simple addition. So if 001 is odd because that's what the law says. It says high output only when the binary number is odd. So A at 001 is only a value of 1. If you go to 010, 1 is at a value of 2. And why do I say that? Because A is 1, B is 2, C is 4, and if you had a D, that would be 8. So that's technically how you're coming up with a decimal.
I get your explanation. So I was imagining a 0 in the spot where column D would be, so that I could make it into a 4-digit binary number where it read 0, 1, 2, 3, 4, 5, 6, 7.
Yeah,
And so
just,
I thought the output was 0, 1, 0, 1, 0, 1, 0, 1.
yeah,
but I see
just
what you're
kind of
saying.
stay. Yeah, let's go ahead and just stay with binary notation. So you just take 0 plus 0 plus 0, which is 0, which is even. The next
Right.
line would be C, would be 0 plus 1. So that's 1, which represent odd. And the next line below says 0 plus 1. So that's 1 plus 0. That would be still 1. 1 is odd.
Right.
So therefore, this one is represent 1 right here. Okay, so you got 0, 1, 1. Okay, now you got the next line. So 0 plus 1. So that's 1. 1 plus 1 would become even. So therefore, that should be 0. Okay, so now you got this one. Here's 1 plus 0. So that's 1. Okay, that's odd. Okay, now you got a 1, 1. So therefore, that one's going to be even.
Right. Okay.
Okay.
That's exactly what I was looking to find out. We're using binary addition.
Yeah, just binary addition, and then at the end we just determine, is it even, is it odd?
Okay, that makes sense. Thank you so much.
You're welcome.
Okay, any more questions? Otherwise, go back into yesterday. Okay. Okay, now we're talking about a full-way rectifier. We're already talking about half-way rectifier. Okay. I try to explain to you. This is your input here. Before, the output they only rectify positive only. That's what they call halfway. Or they can be rectified negative only. Halfway. And now, if you're looking at the output, they will be rectified positive. And also they will be rectified negative. That's what they get the name full-way rectifier. So when you're looking at the input-output, you know that the circuitry will be a halfway or the full-way rectifier. And now go into the circuitry. You can see the circuitry here a little different. Transformer. Transformer, they using the center tap transformer. That means they divide a half on the up, a half at the bottom here. Okay, that's what they're using center tap. And now they just given you the formula here. However, what we want to know, output frequency equal double input frequency. You get 60 Hertz then the output will be 120 ohm. The reason is, if you're looking at the period for the input from here to here, one period, and for the output from here to here, one period. So basically, this period will be smaller than this one I have. So the frequency will be double. Okay. Practical diode 0.7 volt. And VP output will be equal VP input minus 0.7 volt. If they're using the practical diode. Okay. When we're working on this circuitry, they will be going more detailed. Okay. The thing that you understand is when you get a sine wave coming in. And also, you can get a two sine wave, one on this side, one on the other side. However, if you get this one here, positive, and this one will be opposite. Negative. Okay, just divide by 2. That's just a very general. And now we can go in little detail here. Okay, they given you the V in. This is your V in. Go through the center tap transformer. You can see this go positive, then this will be negative. And the value will be the V secondary here divided by 2. That means a half for the top, for the upper, and a half for the lower. And you can see when you get the positive here, this diode will be turned on. Okay? And at the same time, you get a negative diode will be off. So this will be on, so you get one positive. You can say that will be on. Now, when this is negative, and now this will be positive. So the D2 will be on. So this signal will be coming out. So that's why you get another one. And they keep doing the same thing. That's why they call full wave rectifier. Okay, that's just a little more I try to explain to you. Okay, you get a time, you can read it. How come they come up with full wave rectifier? Which input will make the output rectifier? One side and the other. Okay, and now also a little more detail here. Okay, the V out will be equal V primary. That means divide by 2, and you will be minus 0.7. That's how the output will be look like. Okay, they just a more detail for you. Okay. Okay, now let's get an example. For the circuit, so they want to know V peak of the secondary. You have to tell me what the V peak secondary. V peak secondary, that means the voltage going from this side to this side. Equal what? Someone need to let me know.
Is it 49.3?
How come you get 29.3?
So I took the 100 volt max here, divided up by 2, and then I subtracted the 0.7.
No. Nothing to do with 0.7. They're talking about V peak secondary. That means the voltage are from this side to this side. We're not talking about outside here.
50, it's 50. 100 divided by 2.
You know the formula how to calculate the secondary voltage of the transformer. You take the V primary time, okay, 1 divide 2. That means time for primary divided by secondary winding. That's why you get 50 volt.
It's a step down, correct?
Exactly.
So then you divide by 2, and that's the primary voltage.
Okay, now that's the primary voltage. However, if you're looking for the voltage, just a half, okay? Just a half here. Then you know that they will be 25,
Right,
right?
right.
Half 25. Let's see, they say, so the voltage waveform across each half of the secondary winding and also across RL.
But wouldn't that also consider the value of the diode also, like the first student said? Wouldn't there be a voltage drop because of the 0.7? It technically would be like 49.3 or something like that, or 0.3.
Okay, basically you get 25 volt in here, right? 25 right here. And this one you get 25. So when the 25 positive turn on the diode will be look like battery. That will be plus, that will be minus 0.7 volt DC. Okay, so basically we pick, they will be not 25. They have to subtract 0.7. So 25 minus 0.7. -0.7. So you get 24.3.
So is that what's on the output?
That at this point we are right here. So basically, if you're looking at the signal, that's a VR. And this is 0. So basically, they will be positive. Start from minus 0.7. So they will be go this one. Okay. Okay, now, when you measure the V peak, you have to measure from 0 to the top. Okay, so that's why you get the total from the top here to the bottom here will be 25. However, when you measure V peak, you have to be going from 0. That's why you need to subtract 0.7. Okay, let's see what they say here. You see that? 24.3 volt. When you measure from 0, you see that they measure from 0 to the top instead 25. However, I already showed you, they start from minus 0.7. They going little down 0.7. So that's why you get only 24.3.
So you're saying 24.3 is the V peak?
Repeat. The thing is we peak measure from 0 to the top, correct?
Correct.
And now on this one, they start from minus 0.7 here. So from here to here, 25. However, if you measure from 0, then you have to take 25 minus 0.7. That's why you get 24.3 volt.
Okay, Mr. Pham, I understand all of that. Is 24.3, is that considered a V peak?
Exactly, that's the V peak.
Okay, and the 25, what is that considered?
25, that means V peak, okay? V peak before they go to the output.
Okay, V peak before the output,
Right. That means before you go to the diode.
Okay, got it.
However, what I'm saying is, when they positively turn on diode, then you have to know you get the two voltage. One will be sideways, another one will be minus 0.7 volt. So that's why when you draw it, you have to see, you can get the okay, when you draw it, you see this is 0. Okay, And now, when you draw the output here, they get two signals. One negative 0.7. Then you need to draw negative okay? And the signal will be start from here. They go up, go down, okay? They go up, go down. Okay, now you want to measure V peak for the VO. You have to measure from 0. That means from here to here. So basically from here to here, you get 25. However, when you measure from here, that means you have to subtract 0.7. That's why you get 24.3 volts.
And for diode 2, it'd be just the reverse.
Which one?
For the second diode, it would be reverse.
This diode right here.
Yeah, D2.
Okay. When this on, this will be off.
Right.
When this off, this will be off.
Right.
So that's why you get full work.
Mhm. And all the measurements and everything you did would be reversed for D2.
Yeah, both they have to revert it.
Right.
One positive, the other one negative.
Right. Got it.
Okay, so now we come up with another one, still full wave, rectifier. But this will what they call a bridge rectifier. First thing, they using a transformer, just a normal transformer, not center tap. You understand that a center tap transformer cost a lot of money. Okay? So they using 4 diode. They make a bridge rectifier working like full wave rectifier. So you understand the diode may be 10 cents for each watt. So basically they don't want to using the center tap transformer. Got a lot. So that's why normally they using the bridge rectifier. And they working exactly same center tap transformer. And now, if you get an input positive here, okay, that means you get a positive. Which diode will be on? If you can say D1, okay, D2, D3, D4. So for the positive at this point, which diode will be on?
On, Mr. Pham, on.
D1, D2, D3, D4. Which one? Tell me. Which D?
On D2 and D3.
D3 on.
Yeah, on.
Okay, you said D3 on.
And D2. and also D2.
Okay, the thing is positive and this side will be rounded. So that's why D3 on, correct? And another one. Okay, quick D,
D2.
D2. It said D2 also on. Now D2 right here. How come this D2 on?
The positive cycle, D2 and D3 will be forward biased.
I understand how, but my question, how come you say they on? D2 on?
Uh,
Who knows? Telling me. Okay. Now, when you get on this side positive and the other side will be negative. Okay.
Hey, Mr. Pham, we couldn't see what you just did. Can you use your pointer? Your pointer?
You mean on that one?
Yeah, whenever you do something, you just use your pointer, so we'll see.
Okay. So basically, when this side positive, the other side negative. This positive and this will be rounded. So turn D3 on. Okay. Then also the same time, this negative here. And this is a round. That's how come telling you D2 also be on. Okay. So D2 also be on. So when you go into this negative cycle, and this will be positive. That they will be telling you D1 and D4. Will be on. Okay. The thing is when you get a negative here, this is a round, D1 will be on. When you get a positive at this side round, D4 will be on. So that's why you get a full wave rectifier. Now they give you a more detail here. Okay. Try to telling you, okay, which one will be on. So on that one here, so they talking about D1 and D2 on. So that's why you get this output. Okay. And this one, they go to another one, the other side. Okay. They will be telling you, okay, D3. Now let's see. D3 and D4 will be on. So you get another one, depending on which one you go D1, D2, D3. But they will be on 2 diodes at a time. Okay. And now, for each diode will be 0.7. So in order to calculate the output, V peak output, they will be equal V peak of the secondary here, okay, minus 1.4 volt. The thing is, each diode on 0.7, two diode on, you get 1.4 volt. That is the formula for you to calculate the output of the bridge rectifier. There's an example here. Let's see. For the bridge rectifier circuit below, the transformer is specified to have a 12 volt IMF secondary voltage for the standard 110 volt across the primary. Okay. So basically, secondary here, they given you 12 volt. Okay. They want to know what is the peak output voltage. So you know the formula here. V peak out equal V peak of the secondary minus 1.4 volt. Okay. Let's see what happened here. Capacitor input filter. Now, for this circuitry, they connect the capacitor here. Okay. When the input positive keep going, so they keep charging for capacitor. Okay. Initially charging of capacitor. Diode is forward bias. Okay. The thing is at the beginning, you get a 0 here. And now when you get a positive signal, that's a positive. And diode turn on, and the capacitor will be charging. Okay. Diode is forward bias. Happen only when once power is turned on. Okay. When the power turn it on, then they charging capacitor. Okay. So you can see 0 here, they keep charging. However, if the diode on again, remember, you have to get the battery. Okay. This side positive, this side negative, 0.7. So at this point, you get a 2 voltage. One will be minus 0.7, and the other one will be the sideways. Okay. So you can see that the voltage at T0, they will be charging up. See what happened next. Okay. Now, when
Mr. Frank, can you go back to that and show where the voltage is at? Where that red arrow, okay, you got 0.7, okay, but what other voltage is there?
now they keep going. They keep charging.
Right,
Voltage charging on the capacitor.
right.
However, on this one, okay, they will be start from minus 0.7, and they keep going. So that's why the voltage at this point have to be taken. Input must be minus to 0.7 in order to get a V peak.
What's the V peak? What's the V peak in? V peak in, what is
Yeah.
that?
This is they're talking about this one.
Okay,
That V peak in. Okay,
All right,
when they positive, they turn on the diode, they charging the capacitor,
got it.
and they keep charging. You see that?
All right,
Now, you can see they keep charging, okay? And up to this point, let's see, the capacitor discharge through IL. That's the IL right here. After the peak of positive alternation, when the diode is reversed bias, okay? So basically, when you go into the negative here, okay, diode will be off, right?
mhm,
They're not charging anymore. Can you follow that thing? When you get the positive, turn on the diode, will be charging voltage on the capacitor, they keep going, okay? However, when they go to the negative cycle here, the diode will be off, open, okay? What happens if the diode off at the output?
discharge.
They will be discharging. So that's why you can see they go going down. Keep discharging through the load, okay? The discharging occurs during the portion of the input voltage indicated by the solid blue curve, okay? So they go to the top here, they going down, then they will be discharging. And they keep repeating, okay? That's how you can look like. You see that? They go charging, then they discharging, and charging again, and discharging, okay? Like the ripple means less effective filtering. We already telling you last time, this signal will be a ripple, and that will be the noise. You don't want it. So less ripple must be better. So that's why they say larger ripple means less effective filtering. Smaller ripple means more effective filtering. Generally, the larger the capacitor value, the smaller the ripple for the same input and the load. So you want less ripple using the larger value of the capacitor. Okay, so that's just try to display for the ripple here. And also, they want to calculate the V ripple. We don't care. We don't need to calculate the V ripple right here. Only thing is, when you're working in the lab, they want to measure the ripple voltage. Now I can tell you from here. What type of voltage? What voltage you take?
0.7.
No. They will be DC voltage. Okay, they can be 5 volt, they can be 10 volt, 12 volt. On the top of that voltage, you can get the ripple. So I can see example. You can take 12 volt DC. Okay. And basically for this signal here, they can be 2 millivolt. So when you're working on the lab, they want to measure this ripple. How can we do it? How can we measure it?
Pressure delta.
AC coupling.
Can you repeat again, Mr. Smith?
On the scope, you have two things, AC and DC coupling. If you want the AC, put it on AC coupling.
Okay, exactly. Now, if you don't know how to use in the scope, then you cannot measure that signal. How come? The thing is DC voltage is too big and this ripple is too small. So that's why if you can display a DC and the AC, then you cannot see the ripple. And if you want only measure the ripple, you have to set your scope to AC coupling. AC coupling tries to remove DC, no more DC. That's why you can see the big ripple. When you're working on the left volt, you must to do it. You see that? That one they given to you a little more detail. From here, go to here. That's a DC voltage. Okay. And we rectify from here to here. And this is a ripple here. This is a ripple. So if you want to measure the ripple, you have to set your scope to AC coupling.
Question,
they-
Mr. Pham.
Yeah,
So when they asking for the measurement of the ripple, they only want it from, not from zero, but from where it starts charging to the discharge, from charging to the discharge?
right,
Just that measurement, not from
Right.
zero?
exactly. From here,
Okay, thank you.
only this one. Nothing from zero. Okay, if you're looking on the oscilloscope, you set DC coupling. What happened? They're supposed to be displayed signal look like this one. DC coupling will be displayed both DC voltage and AC voltage. However, DC is too big, so that's why you cannot see that too small here. So in order to measure the ripple only, you must set your scope to AC coupling. So they remove that DC, and you see they going down here, display right here. So you can see the ripple to measure. Okay, so now basically will be almost run out of time. Today, Sam, we get the queen number 3, right?
Yes, sir.
Hello, Sam.
Yes.
We will be
Go
running
ahead, Mr. Pham.
queen 3 today, right? You ready for that?
Yeah, I do have quiz number 3.
Okay. Now, on this one. Okay.
Yes, I do have quiz number 3 ready.
Okay. I think if you follow it, that will be not a problem. Okay, first thing, okay, they calculate the V primary, big primary. So you know you get 115 volts.
Yeah, it's all broken. It was,
Yeah.
so he's back.
Because it might be a little bit of a big ask. Okay. Let me think here. NTS CDV.
Are you back, Mr. Pham?
Turn your mic on, Mr. Fran.
Give him a moment to get himself together. Okay, you're back, Mr. Pham.
You need to turn your microphone on, Mr. Fran. And your speaker.
Okay, for some reason, my computer, they try to connect again. So that's
Okay.
why. Okay.
All right.
You need
Anyway,
to turn on the recording.
Recording is still on.
yeah, the recording's still on. I think so.
Yes.
Okay. For this circuitry, I just given you the idea. They want V peak at the primary here. You already get 110, 15 volt IMS. You must be converting to V peak. That's the first thing. Second thing, they run VP secondary in here. Okay. They get a ratio 10:1. Easy to know. The unfiltered peak full wave rectifier voltage. Okay, that means they want to calculate the output for the bridge rectifier. You already know they will be V peak secondary minus 1.4, and the frequency output input frequency 60 hertz. Output will be double. Okay. Okay, lucky. Thinking next time we'll be stuck with another one will be bipolar transistor.
Okay.
Okay. So now Sam will be run the quiz number 3.
Okay, ready when you are.
I try stop this guy.
Yes, sir. Okay, so make sure you download the quiz from the website. Okay, so let me go ahead and share my screen. Okay, so make sure you go into the website and just go to the handout. Make sure you download the answer sheet for DC Quiz 03 Spring 2022 report. Okay, so now that's taken care of. Okay, let's go ahead and run the test. Okay, slideshow, start from beginning. Okay, there we go. Can y'all see?
Yes, sir.
Okay. Okay, so that's pretty much it. So make sure you upload it before 12 noon tomorrow. Let me go ahead and stop the sharing. See what's on the chat there. 1 second. Let me see what was on the chat. Can you see number 13 again? Okay, just one more turn, 13. Okay. Let me back into my slide, number 13. Okay, share screen. Let's start from current slide. Okay, that's 13. Okay. Let's stop the sharing. Let's see what's up in the chat. Okay, so that's pretty much it. So make sure you upload this onto the website. It's due by 12 noon tomorrow. Okay. All right, that's it, Ms. Pham. Thank you very much.
You said,
You're
Thank you,
welcome.
sir.
okay, now, that I finish for anything regarding to very practical DC circuitry. From the next quiz will be covered in electronic. That means diode, Zener diode, okay, full wave, half wave, bridge, rectifier, okay? And we'll be see you on next Tuesday. We don't have a class on Monday, next Monday. That's holiday. Okay. And we will see what's going on, what's coming up to the in-class lab. I still waiting for the dean will let me know what's supposed to be. Okay? So, any question to me? If it's not, then will be good night for everyone.
Good night, Mr. Pham. Good night.
Good
Thank you,
night.
Mr. Pham. Good
Good
night.
night.
Good night.
Good.